Hello everyone, and welcome back to this lecture session on BSP 303, that is Digital Systems and Applications. So in the last few lectures, we have already covered the basics of digital systems and application, which also includes the starting of, the logic gates. So in the last lecture, I have taught you about the OR gate. So we will continue our discussion, and further we will discuss about the basic gates, which also includes the AND gate and the NOT gate. So in today's lecture, I would like to cover about the AND gate and the NOT gate. So without wasting much time, let me share the screen and let me start the presentation straight away. So here we go. So this will be our today's discussion on the some of the basic gates, that is the AND gate and the NOT gate. So I have already pre-written the presentation which I am going to do today. So yeah, so let us start discussing from the AND gate. Here you can see the AND gate, and before we actually go to the AND gate, let us first see the AND laws. What are the different AND laws? Okay, so here I have written that if you have any variable ANDed with 1, then you would get the same variable. I'm sorry, I think I have written it mistake here. This should not be 1, this should be A. Okay? So if any variable is ANDed with 1, you would get the same variable. And if any variable is ANDed with 0, you would get a 0. All right. So these are the two AND laws which you should remember before we actually go to the AND gate. All right. So first, let us see the symbol for this AND gate first. So here I have drawn the symbol for this AND gate. You see. So there are two inputs here, A and B, and we have one input. Now, sorry, one output. So the output would be high when only if both the input are high. Okay, when both the input are high, then only the output would be high. Otherwise, for any other combination, the output would be 0 as per the AND laws. And I have drawn the truth table for the same symbol which I have drawn on the left hand side. So here you can see that when both the input are low, the output would be low. When any one of the input is low, then also the output is low. Okay, so the output is high only when both the inputs are high. Only when both the inputs are given some positive potential, then only you will get a positive potential at the output. Otherwise, you will get a zero potential at the output. Okay, so these are some basic things which you should remember. Now, before we go further and try to build this AND gate with diode and transistor, so let me first show you the switching circuit for this AND gate. Suppose we have a simple switching. Suppose I have a simple switches. Let us say you can see this figure here. A and B. Suppose this A and B are two switches. Okay, and then if you connect these two switches in series in this way, and the output, this one is the bulb. Let us say this X cross the mark X is the bulb. Now the bulb will glow only when both the switches are closed. Okay, I hope you got it. Only when let me put these switches closed here in this way, and then this switch be also closed. Now when both the switches are closed, then only the current can, the electrons will flow, and then the bulb will glow. Otherwise, when any one of them is open, let us say when B is open, okay, A is closed. That means A is 1, B is 0. Okay, in that case, the bulb will not glow because current cannot flow through this open circuit. Similarly, when both are 1, 1 also. Similarly, when both are 1, 1, sorry, when both are 0, 0. In this case, both are, we can say that the switches are open, so they are 0, 0. Okay. In that case, also the bulb will not glow. The bulb will glow only when both of these are closed, when both of these are 1. Okay. So this is a very simple switching analogy of the AND gate or the AND law, you can say. Okay. So this is the very basic discussion about the AND. Now let us go forward and see how we can construct the diode AND gate. How we can make AND gate with the help of a diode. Okay. So here you can see this circuit where the two diodes, let me call these diodes, okay, let me just call these diodes as D1 and the lower one as D2. They are connected in this way. The diodes are connected in this way. So now when you give both as 0, 0, when you give both as 0, 0, what happens? Let us see. So when you are giving 0 to A, that means the diode D1 is reverse bias, because you see that this is the P side of the diode. Okay, this is the P side of the diode, and the P side of the diode is connected to this plus potential, plus 5 volt, and N side is connected to lower voltage, that is the ground potential. Okay, so that means the diode D1 is forward bias, and similarly the diode D2 is also forward bias. So in this case, what happens now? Since the diode D1 is forward bias, the current will flow through this diode. Okay. Similarly, the diode D2 is also forward bias, so the current will flow through this diode. As a result, what happens? All the voltage drop, that is 5 volt, it will drop across this R, and this point would go to ground potential. Let me call this point as N. As a result, since the current is flowing through both the diode, the point N will go to ground potential, that means the 0 volt. That means the output will also be 0, because the output Y is connected to this point N. Okay, so this is the condition when both are 0, 0. Now when any one of this is 0, any one of the diode is 0, then also the output should be 0. So let us check this, and the diodes are connected in parallel, you can say here. Sorry, so this should be D2. Yeah. So now when, let us say when A is 0 and B is 1. So when A is 0, the diode D1 will conduct, because the diode D1 is forward bias, so the current will flow through this diode. Okay. However, the point B, you see here, I am giving 1 volt. That means some positive potential I am giving. That means the positive potential is given to the N side of the diode. Remember, this is the N side of the diode. So that means the diode is reversed bias. Current cannot flow through this diode, the diode D2. Okay. But however, the current is still flowing through this diode, and the current is flowing through this diode means now also this point N will be driven to ground potential, because whatever is this plus 5 volt, everything would be dropped across this resistance R, and nothing would appear across on this point N. The point N will be still at ground potential. That means the output would be again a 0 volt. Okay, the output will be high only when both of these are high. So let us see what happens when both of these are high. Okay, suppose I'm giving 1 volt here, that means some positive potential. I'm giving 1, logic 1, and on B also I'm giving logic 1. Both of these are, A and B, are at some positive potential. That means the diode D1 is reversed bias, and the diode D2 is also reverse bias. So current cannot flow through this diode in these conditions. Okay, current cannot flow through this D1 and as well as D2. Now what happens? You see, current, since the current cannot flow through this diode, that means whatever is this potential plus 5 volt, it will not be dropped across R. The same potential would be appearing across this point N, because the current is not flowing through this resistor. Okay, now the current is not flowing, that means nothing would be dropped across R. Whatever is this positive potential, everything positive potential would appear across this point N. That means the point N would be at a positive potential now. And since the point N is connected to Y, so therefore the Y will also be at some positive potential. That means it is at logic 1. Okay, so in this way, a diode AND gate work. Okay, I hope it is clear. So let us now go forward and try to design an AND gate with the help of a transistor. Okay, so I'm just going to the next slide. Yeah, Here we go. All right. So let us see this diagram carefully. So I'm going to name these transistors. So let me call these transistors as Q1, Q2, and this the last one as Q3. Okay. So you know that the working of the transistor, as I have already discussed, this is an NPN transistor. N base is P and emitter is M. Now for this transistor, if you want some current to flow through this transistor from collector to the emitter, then you need to give some positive potential here. If you give some positive potential to the base, since this is an NPN transistor, then only the transistor will work. That means the current can flow from the collector to the emitter. Okay, so let us see this case. When A is 1, logic 1, B also logic 1, we should get a logic 1 at the output. That means a positive potential at the output. So when both A and B are 1, 1, that means the transistor Q1 is working, isn't it? Because I'm giving some positive potential to the base of this transistor. So the current can flow through the collector to the emitter. Okay? And then now B also, same thing. The current can flow from the collector to the emitter. So in this case, when both of these are 1, 1, the transistor Q1 and Q2 are working. So in this case, what happens? Let me draw the current will flow through the point N, and the transistor is working. So it will flow from the collector to the emitter, and again from the collector to the emitter, and then it will flow ground. Okay. So this is the direction of the flow of the current. Since both the transistors are working, the current is flowing from this point to the ground. Okay. That means what happens now? You see this point N very carefully. Now, since the current is flowing, that means all the voltage would be dropped across R1. All the voltage would be dropped across R1, and nothing would appear at this point M. That means the point N is at zero potential because the current is flowing through this transistor and all the voltage is dropped across R. So nothing would appear across N, this point. So this point is at zero potential. Now you see that this point is connected to the base of the transistor Q3. Okay. This point is connected to the base of the transistor Q3. That means since this point N is at zero potential, that means the transistor Q3 will not work because you are giving zero potential to the base of the transistor. So therefore the transistor will not work. Okay. Now if this transistor does not work, current cannot flow through the emitter to the, like this, current cannot flow. Okay, I'm just writing X here. Current cannot flow through this transistor. That means what happens? Whatever is this voltage, all the voltage would be appear across this point M. The point M would be driven to a positive potential, and as a result, since the point M is connected to Y, then Y will also be a positive potential, that is at logic 1. Okay, so when both of these A and B are 1, 1, you will get a logic 1. When any one is 0 or both are 0, then you would get a 0 output. So let me explain you that condition also. Any one of the three conditions, I'm going to explain you. Let us assume that, okay, let us assume that A is 0 potential and B is 1. Okay, so I'm giving 0 potential to A, that means to the base of this transistor Q1, I'm giving 0 potential, which is an NPN transistor. So this will not properly forward bias the transistor. Okay, this will not properly bias the transistor. That means what happens? The transistor Q1 will not work. Even though the transistor Q2 is working, so it is meaningless. I mean, if the transistor Q1 doesn't work, no current will flow through this one. This Q2 will not get any current. Okay, so Q1 will not work. That means whatever is this potential, I mean, since the current cannot flow from here to the ground, whatever is this potential, it will appear across this point N. Okay, that means current is not flowing, so the point N will be driven to this positive potential. Okay, and since the point N is connected to the base of Q3, that means the base of Q3 will get a positive potential. Okay, now if it is getting a positive potential, then the transistor Q3 will work. Now you see here, if the transistor Q3 works, what happens? If the transistor Q3 work, that means the current will now flow from here to the ground like this. Okay, in this way the current will flow. Now since the current is flowing through this transistor Q3, so whatever is this voltage, it will, all the voltage would be dropped across R2, and as a result of which the point M will go to zero potential. Okay, because the current is now flowing through this point to the ground, to the ground potential, from positive potential to the ground potential. That means this point M would be driven to ground potential. Okay, and as a result the point Y is also at 0 volt, or you can say it is at logic 0. Okay, so in this way, if both are 0 also, same thing will happen, and if anyone, either A or B, if B is 0, then also the current cannot flow through this path. Okay, and as a result, whenever the current is not flowing through any one of these Q1 and Q2, the current will be flowing through Q3, and the output would be 0. Okay, so for the output to be at logic 1, for the output to be at logic 1, both of these transistors should work, otherwise it will be at logic 0. So this is all about the AND gate and the construction of the AND gate using diode as well as transistor. So let us see another type of gate, that is the NOT gate. Okay, let us discuss about the NOT gate. So before we go to the the construction of the NOT gate using transistor, let me tell you some of the few NOT laws. Okay, so these are some of the NOT laws. The complement of 0 is 1, 0 complement is 1, and 1 complement is 0. Okay, and if you double complement any variable, you will get the same variable. For example, 1 complement क्या होता है? 0. ठीक है, फिर 0 का complement क्या होता है? 1. The meaning of this one is that if you double complement 1, you will get the same 1. Okay, so if you double complement 0, you will get the same 0. Similarly, if you double complement the variable A, you would get the same variable A. So these are some of the important laws, NOT laws, which you should remember before we go to the NOT gate. Now here you can see I have written the symbol for NOT gate. So this is the symbol for NOT gate. Unlike other gate, NOT gate will have only one input. Okay, because the other gates are at least minimum having two inputs, but in case of NOT gate, it will just have one input and one output. Okay, so if the input is A, the output of the NOT gate is the complement of A, that is A complement. So based on this one, we can draw the truth table. So in the truth table, we will have only one variable as the input, that is A, and we have Y as the output. Now A can have two values, that is 0 and 1. I have written here 0 and here as 1, isn't it? So when the input is 0, output is 1, and when the input is 1, output is 0. Okay, this is a very simple truth table. So it will be very easy to remember. Now let us go and try to design this NOT gate with the help of some transistor. Okay, we just require a single transistor to design it. Before we actually go and design the the NOT gate, let me tell you the switching circuit first. So here you can see this switch A. Okay, so and there is a cell connected here, and this is the bulb. This output indicate the X mark indicate the bulb. Okay, so now here whenever the switch is closed, the bulb will not glow because now the switch is open. So what happened? The switch is open means the current will flow. The current will flow like this because the current cannot flow through this switch. As a result, since the current is flowing through this path, okay, the bulb will glow. Now the other case, let us see when the switch is closed. Suppose when the switch is closed, in this case what happened? Current will go here. Current will have two paths to go. One is this one and the other is this one. But since, of course, if any load is connected at the output, there would be some resistance. But here there are no resistances, so the current would like to go through this less resistance path, and it will complete the circuit in this way. Okay, now the current is moving in this way. That means the bulb will not glow. Okay, so when the switch is closed, the bulb will not glow. When the switch is open, the bulb will glow. Okay, that means when the input is 0, output is 1, and when the input is 1, output is 0. This is a very simple switching circuit for a NOT gate. Okay, as we have seen the case for AND gate also. So now, before I actually conclude, okay, let me show you the transistor NOT gate. Okay, so here we see the transistor NOT gate. You can see this circuit here. Okay, so the point A, whenever the point A, let me tell you that the point A, let us say the point A is at logic 0. Now, when you give logic 0 means 0 volt. Okay, so when you give 0 volt to the point A, the transistor will not work, because the transistor will not conduct, because this is an NPN transistor. So this is an NPN transistor, and this side is the emitter. Okay, so for an NPN transistor to work, you need to apply some positive potential to the base. Since I am not applying any positive potential to the base, the transistor will not work. Now, when the transistor will not work, current cannot flow from this positive potential from the collector to the emitter. Current cannot flow through this transistor. What happens then? If the current cannot flow through this transistor, whatever is the voltage, all the voltage would appear across the output. That means the output would be 1. Okay, I am applying 0 at the input, I am getting 1 at the output. Now let me tell you the other condition. Here. That means when I am giving a logic 1 at the input, that means some positive potential. So the transistor will work. In this case, the transistor will work. As a result, what happens? Current will flow like this to the ground. Okay, so the current will flow. Since the current will flow, let us call this point as N. Since the current will flow through this transistor, so all the voltage would be dropped across this R, and the point N would be driven to ground potential, that is 0 volt. Okay, now since the point is driven to ground potential, the output Y would also be at ground potential, that is logic 0, or you can write 0 volt. Okay, so in this way, the transistor NOT gate works. Okay, so this is about the part 2 of the the logic gates. So in the next discussion, we will try to see some of the other gates. Those are known as the universal gates. Okay, so today I'm just I will have to stop the lecture here. So thank you everyone for joining the lecture. So in the next class, we'll try to discuss about the universal gates. Thank you.